Hello everyone and welcome back to the channel. So today we are going over another example in the Basics of Static Equilibrium series, and this time we are just going to solve a problem with a hinge in the middle, but it's going to be slightly more complicated. But without further ado, let's just get started. So as you can see, the point here, we want to solve for reactions at A and at E. Alright, so the way we are going to do that is like with any other hinge problem. First, or any other problem as a matter of fact, first we have to identify which reactions we need to solve, which is AY, AX, EY, and EX. Alright, so let's just since this is a problem with a hinge, we are okay to break it up into two systems, all right? So one system is going to be this half. Let's move that down here. And the other half is going to be this half, all right? So we can split this up into two systems and solve them separately, but just remember that this distributed load has to go on both of them. All right, so just to make you guys not confused as much, we'll just erase right up until this point over here, right? And then we'll do the same for this side. All right, so once we have that down, have that set up, all right, the next step is just to solve it as any other problem, all right? So when you split a hinge like this, always remember to have the reactions at that pin or hinge, right? So in this case, I'll just set CY, CX as upwards and to the right on this side, and then for the other side, we can just do the opposite thing, all right? So that when you piece these two together, they would just cancel out, all right? It doesn't matter if this side is upwards, but just equal and opposite, all right? Just remember that. So once we have that, we can just go through our equilibrium equations. So I'll just start with the segment AC, all right? So let's just get to it. So sum of moments, right? Take a moment around A, and that equals 0, all right? So the forces here, I can relabel it really quickly. So this is 40, sorry, that's not 40, that should be 20. 20, and then up until here is 10, and this is 20, okay? Since we split it up. Since sum of moments around A is equal to 0, right, we have to just consider all the forces that are going in it, right? So first up, I'm looking at the 6 kilonewtons at B, and that would be 6 times 20, and because it's rotating it clockwise, it would be negative, all right? Next thing would be from the distributed load, so that equals 0.4 kilonewtons per meter times 20, the total distance here, right? And then times 10, which is, if you're replacing it with a load at the center, it would just be half of this distance, all right? Keep that in mind. And then that is also pushing the system clockwise, so that would also be negative, all right? Next is, let's go for this CX value, all right? So CX wants to, again, spin the entire system clockwise, so it would be negative CX times the perpendicular distance, which is 30 meters. All right, and then finally we have to account for CY, right, plus CY because it wants to spin it this way, right, counterclockwise. That's positive, so CY times 20, and then all of the forces are accounted for, so we can just set that equal to 0, right? Now, if we simplify this, right, this is negative 120, and 0.4 times 20 times 10 is equal to negative 80, right, and then minus 30 CX, and then plus 20 CY equals 0, and then that's simplifying it even more. That's 200 on this side, and then minus 30 cx plus 20 cy. All right. So I guess we can factor out a 10, right? So just dividing everything by 10, which makes it a bit easier. Cx plus 2cy equals 20, right? And that's your first equation, right? Notice that we can't solve it yet because we only have one equation and two variables, all right? So next we can just do the same. Now how do we get the second equation? We can just do the same thing, but for beam segment C all the way to E, all right? So once again, we can just take a sum of moments around E, right? Sum of moments around E, counterclockwise equals positive, and set all the forces to equal to 0, right? This side's just slightly easier. We have only 3 forces to account for. So let's go with the 0.4 kilonewtons first, right? 0.4 times this distance is 20. Times 20, right, times 10. This wants to spin it counterclockwise, so that is positive, right? Plus cy, cy is 20 times cy, right, that's perpendicular distance, cy, right? And then that wants to spin it again counterclockwise. Every force here is actually spinning it counterclockwise, so next is cx, so that's 30 cx, and that should be positive. That equals 20, all right? So once we have that, we can just do 20cy plus 30cx equals negative 80. Move this to the other side. So 2cy plus 3cx equals negative 8, simplifying here, all right? So once we have these two equations here, right, we can just solve that. So let me just rearrange these two equations. 2cy minus 3cx equals 20, and then the second equation is 2cy plus 3cx equals negative 8. All right, so for this example, we don't have to do any substitution, just add the two together and it should work. All right, so that's 4cy equals, and then 20 plus negative 8, that equals 12, and cy you get 3 kilonewtons, okay? And then once you have 3, it's very easy to calculate the rest. Just plug it in any of the equations. So in this case, I'll plug it in the first one, and you get cx equals to, let's see, 6 minus, so 20 minus 6, 14, negative 14 divided by 14 divided by negative 3 is equals to 4.67, or what is that in 14 over 3. Okay, so is this negative? Well, yes it is. Okay, so let's go back to this original system. Now that we know cy equals to 3 kilonewtons, and cx is equal to negative 4.67. All right, we can just go back and solve these individual systems. All right, so once we have that, we can just do sum of forces in the x direction for beam segment A, and we should get let's see, cx is negative, it's going that way, so ax would equal to cx, right? Because ax plus cx equals, oh, and then plus the 6, don't forget the 6 equals 0. So then we have, let's see, ax equals negative 6 plus 4.67, and that equals like 2 or 1, or 4.67 minus 6. That's equal ax equals to negative 1.33 kilonewtons. All right. Then sum of forces in the y direction for this beam. All right. We have ay plus cy minus 0.4 times 20 equals 0, right? And that would just be cy equals 3, so ay plus 3, and then 0.4 times 20, so minus 8 equals 0, and then ay would equal 5, right? So once we have that, we can move on to the other half of the beam. Ooh, do I want to start a new page? Should be fine. So now we can just do the same thing on the other side. So we have 0.4 times 20, and that's negative going down, and then minus cy, and then plus ey would then equal to 0. So we have, let's see, negative 8 minus 3 equals negative ey, and then ey would just equal 11. And then finally, sum of forces in the x direction equals positive. Well, there's not much work to be done here, but I believe cx, what did we find cx as? Cx equals negative 4.67. So ex would just also equal negative 4.67. All right. So I hope this process made sense, and if it did, that's great. The summary for this time is just when you see a problem, no matter how complicated, with a hinge, just remember, split it up there, and there's nothing really complicated about that. And if you ever see something like this, a distributed load on, let's say, an angle, just always remember that you don't have to adjust for it like this or anything, because that makes it unnecessarily complicated. All you really need to do is just take the perpendicular distance from the force, right? Not that one, sorry, but this one. This perpendicular distance, always just break them up into x and y components, so that when you're analyzing these, it might be a bit tedious, but once you get faster, it'll come very intuitively. All right. So I hope that all made sense to you. If you have any questions, feel free to leave it in the comments below. But otherwise, yeah, that's it for example number 7. Stay tuned for the next video. I'll see you guys later.